And this talk is basically the summary of like these past 5 years, how we started as like a small startup and how we built basically a big data platform to store over 100 petabytes of data while letting our users access this data with minute-level latency. To give you an overview of what the talk would, how the talk would look like, I'm going to start with like a brief introduction in terms of how data is used at Uber. I'll then give you a brief taste of like where we started and what the problem we faced. And then I'll spend most of the time talking about like, our current architecture, how we overcome those initial problems. And then I'll talk about what's coming up next. And I'll try to wrap it up by sharing the lessons like from we made tons of mistakes, we made a bunch of bets, and some of them turned out to be good. I'll try to share that with you so when you walk out of this talk, hopefully you learn something from it. Okay, so let's get started. So Uber's mission is to build a platform that can set the world in motion. That means to build a transportation platform that it can provide a wide sets of different products. So based on different user needs, they can pick their product. And these products are not going to be all provided by Uber. We want to be the platform that gets other companies to also build products on top of this platform. We are a tech company, so definitely data is at the core of all our products. To give you a sense of like how data is like used at Uber, like at any point in time, we are having like several thousand dashboards and reports that basically reviews this data in a meaningful way to different cities, different operators, different teams to make decisions based on those. At any given time, we are running over 500 experiments, concurrent experiments, in terms of what changes we should make, what new products we should try out to make the life and the experience better for our users. We have several thousands services like relying on this data to provide some new sets of services to the rest of the company. For example, the service that provides like the estimates the time of arrival or time of delivery of the food, it uses some machine learning algorithm that relies on the data that we provide. And that service is like serving around like 800,000 queries per second. So that's the scale that these databases are used across the company to make the experience better for the users. So to give you a better view in terms of like how the business grows over time and then the related data grows as a result of that, let's look at the number of trips taken on our platforms. So we started like in 2010. It took us 6 years almost to get to the first billion trips. Then we did the second 1 billion trip within 6 months. The 6 months after that, we did actually 1.5 billion. Right now, we are doing around like 3 billions every 6 months. And we're building a platform. You can see the slope of this line is like exponentially growing. And we are building a platform that should be ready to serve like over like 1 billion trips per month very soon. And this is not just because of like our traditional peer-to-peer ride sharing that's growing. It's because of the sets of new products that we are offering all the time on top of these platforms. So look at this graphic. We started like our traditional peer-to-peer ride sharing in 2010. In 2014, we introduced like Uber Pool. It's not only a new product, it's actually a much more complicated product, both like for the users as well as what's happening behind the scene. If you compare it with a traditional ride, you have one driver, one ride, and a trip happens between 2 points. In terms of Uber Pools, you have one driver, but you have multiple riders getting into the car. So you have to match their routes, you have to match the pickup points, so it's much more complicated and much more advanced products that we offer. In 2015, we started our autonomous cars, our self-driving cars, which these cars, by the way, they are in pilot test right now. If we roll them out in large scale, it's going to be huge amount of data that we generate. We have Uber Eats starting in 2015. Again, this is a more complicated product. Now you have a restaurant involved too. So you have a driver, you have a restaurant, and you have someone who ordered the food. So the trip consists of 2 trips because the driver needs to first get to the restaurant, pick up the food, and then goes to the rider, to the person who went the request to deliver the food. In 2017, we introduced Uber Freight. This is a service that lets companies and people ship packages and goods between different cities. And this year, we actually released a bunch of products, including Uber Bikes. This is the electric bikes that is basically on-demand bikes that are dockless, so you can pick them up for short trips. And we also have Uber Scooters, which provides like electric scooters, and we also introduced Uber Health. So you can see that the range of products that we are offering is actually expanding, and these are the products offered by the company. we are opening up the platform for other companies to build on top of that, so we can expect more and more products to be built very soon. Now in terms of our data users, so first, these are analytical data used within the company. By different people, like different engineers, different data scientists and operators. So let's look at the way we categorize our data users. So we have primarily three categories of our users. The first one are city operators. These are the on-the-ground crews in every city that runs their city. Think about these like basically one startup, one small Uber startup per city, and they are making a decision how they can make the experience better in that city. So they definitely need these data on a daily basis to make decisions in terms of what promotions they run in the city, what priorities they should focus on. So they heavily rely on this data. Then we have our data scientists. These are the researchers across the company. We have several hundred of them. They are focused on analyzing, looking into previous data, and trying to come up with new ideas and trying them out on past data to see what new products we should basically build next. And when they come up with some idea that works relatively okay on the previous data, then they run that as an experiment with A/B testing to see whether it works in practice or not. And then we have the engineering teams and engineers across the company that they use these data, these analytical data, to serve some new use cases, some new services to the rest of the company. Think about, for example, the service that provides estimation for time of delivery, or the fraud detection as a service. So these are the type of services that people have. So if you are having engineering background, you're curious in terms of the numbers. So let's look at some numbers. So we have first we have our infrastructure is basically a tripod strategy, which means we use clouds as well as our own data centers. So these numbers are from only one of our data centers. So you have to multiply that by the number of data centers as well as the cloud providers. So it just a sense of how many basically hosts we are running per data center. We are having 20,000, and that number is a little bit old. So we are having over 20,000 hosts for each data center. That provides 200 plus vCores. We have 100 petabytes of data stored in our Hadoop clusters. We have 100,000s of queries, like ad hoc queries, Presto, Hive, or Spark jobs running per day. And again, our platform generates and processes over 2 trillion messages per day. This is roughly equal, I think, to 12 million messages per second. But that's the scale this platform is running at. So our strategy to build this infrastructure, so these are extremely large amount of data. There are very few companies in the world that are dealing with this amount of data. So in order to be able to build a solution that can support this large scale data, no single company can do that. So the only way to do that is to basically work as a group and collaborate. And we set our strategy to build this platform based on open source stack. That means we borrowed a bunch of components from the open source stack to build our infrastructure, data infrastructure. That includes use Spark, use Hive, Presto, HDFS-like. But when you come to this large scale, many of these technology does not work as is out of the box. It's not just setting it, getting it, configuring it, and using it. You have to go and fully understand what the bottleneck is and try to find a workaround or maybe redesign that component to scale it. And we do that all the times in terms of HDFS and other stuff that we use, and we try to contribute back to the open source to basically help other companies to provide the basic version of those tools. At the same time, there are from time to time there are gaps between what is available in open source, or there are components in the current technology that cannot be scaled. So we have to build some stuff from scratch in the company. And we try to open source as many as those as we can. So specifically from my team, we have open source multiple projects over the past few years. I'm going to cover 2 of them. So 2 of them, Marmari and Hudi, which I will cover within this talk, and they're all open source. If you want later to look them up, you can go to them. So my team's vision, which is a big data team, is to provide the infrastructure that can store and serve 100 petabytes of data in a reliable way as fast as possible to the rest of the company. So hopefully this introduction gets you excited. So let's have a look at where we started a few years ago. So this is our infrastructure, our first efforts to build a big data platform at Uber, and this is from 2015. So it doesn't look like that old, but it's actually pretty old for the way the data growth has been. So at the left-hand side, you can see different sources of data. So in Uber, we have basically two relatively separated worlds. We have an online world, which is all the services and products that are required to make a trip happen. So those are like very super critical services, and they basically work as we try to minimize the number of services involved in that, and those are the ones that are needed to make a trip happen. Anything after that is considered as analytical tools, and they all rely on the data that we provide to them. So these data stores that you can see on the left are the interfaces between these two. So when a trip, for example, happens, that trip gets stored in like a sharded key value store, and then we try to get those data into Hadoop. So we have, as a source, we have different key value stores. We have many services use their single box traditional RDBMS databases like MySQL, Postgres. And we also use Apache Kafka a lot across the company as a message queue between different services, a buffer between different services. And we do have like different source of data. So these source of data are brought into Hadoop through a bunch of like ingestion jobs, Spark jobs that we wrote, and that we're bringing this data and enforcing schema to make sure we only bring in the high quality data and storing the data in like Apache Parquet format. So for those of you who are not familiar, Parquet is like a columnar file formats. So we are bringing huge amount of data into Hadoop. If I give you an example, for example, our trips table, it has several hundred columns, each 5, 6 columns nested. When you bring this data into Hadoop, most of our users, when they try to access this data, they do not need all these 100 columns at once. So they usually are interested in 1 column, 2 columns, or maybe a few feeds from a few columns. So that's the reason that when you're dealing with big data, it's best if you store them in columnar file formats, because that's optimized for accessing only the data and reading only the data that users need from this. At the same time, when you basically store the data on these in columnar file formats, the data that sits next to each other on these are at the same time, so your compression ratio would significantly go up. That's huge amount of saving in terms of your storage space. So anyway, so we use Apache Parquet for storing our data. And then we have our data modeling are happening within Hadoop. So these basically model the tables. So these are raw tables, and there's modeling happen on top of those. It's stored basically schema, and they generate model tables that are stored back into Hadoop. Now, in terms of the users, they can access these data directly through Hadoop, through the query engines that we provide. We provide Hive and Presto as the query engines for ad hoc queries. We also provide Spark and notebooks for people who wants to run program, what needs to write code to access this data. Also, a subset of our data, mostly our very recent data, gets loaded into our warehousing tools. This is mostly used for these city operators that they need to run the queries, a lot of queries, but they are pretty short and they only need recent data and they want to run the query as fast as possible. So this is the platform that we built in 2015, and that lets us to store a few tens of petabytes and the data and provide a data latency at around 24 hours. So if a trip happens today, it takes 24 hours for that trips to be available to our analytical data users. So in terms of but this was, again, it seems like an old technology, but by the way, this is used a lot at this time across many different companies. So it's actually a classic way of bringing all the data in. But for us, it was a big win because it was the first time we had all our analytical data in one place. So Hadoop being the source of truth for the rest of the company, our data was a game changer. Before that, if someone needs to, for example, join our trips with our transactions, they have to write codes that access the database storing trips and write codes to access the other ones and join them through the code. It was really painful to make big analysis on this data. So this was the first time you had all this data in one place. So a lot of services start being built around this data. And again, we had column formats to improve the efficiency in terms of storage and servings. And I think I covered all this stuff. But obviously, this was old technology for us. So there were a bunch of limitations that when this becomes popular, there were more data that were brought into Hadoop. So our data size starts growing, and people have certain needs that this couldn't address. So in terms of summarizing the limitations, the first one is scalability. So the scalability was showing up both in terms of the HDFS, which is the Hadoop file system that was used to store this data, as well as those jobs that were ingesting data into Hadoop. So I mentioned that those jobs were bringing data from different sources, and we had actually it was not a platform, it was a bunch of ad hoc jobs that people wrote to bring their data into Hadoop. It was working fine, we were dealing with a few tens or hundreds of tables, but then we had several thousand of these tables being routed into Hadoop, and having like an ad hoc job is not scalable. We had a large team just trying to fix Apache stuff to make the data flow. Users were super unhappy because the data was very not reliable. You didn't know when the job is going to be succeeding again. At the same time, it was operationally very expensive to scale that. The second problem we had was data latency. I mentioned that we had all the data in one place, but the latency, the new data showing up was 24 hours. For a business like Uber, which is by nature real time, this is very slow. Think about like a city that wants to run out to send out some promotions, for example, in terms of giving free rides or some sort of promotion. Most cities, they have some budgets to spend, so they look at the previous few weeks and they come up with some promotions and they start rolling it on Monday. So they want to know how that promotion is changing the flow of trips in their city as soon as possible. If they wait for this data to show up in Hadoop 24 hours later, and they spend a few hours trying to analyze it, by the time they have the result, it's like basically 2 days past. And they have spent a lot of their money already without knowing how it's going to help. So they wanted to know the results as soon as possible, hopefully within less than an hour or two, so they can revise the promotion as they go. So that was the second problem. The third problem was we had updates. So our data, so traditionally all the Hadoop platforms, the idea is it's basically append-only data. So you write stuff and then later decide how to deal with it. And this is basically because when Hadoop started, it was, for example, used by Facebook, for example, to track the click-throughs on clicking on ads. So these are append-only data. Our data, by nature, they have a lot of updates. And we had to solve that problem. We also have the data arriving data. So the combination of those two makes basically try to hide the problem by coming with workarounds, but later we found out that this is actually a natural part of our data and we need to build a solution that can solve this problem rather than hiding it. And finally, our modeling, it was basically in snapshot based, which means the source tables gets updated, the modeling happens again, they create a new model tables, and they update 2 tables in production. And this is very inefficient because you are regenerating the whole tables because of the peak records being updated. So let's look at like what I mean when I say update is like natural part of the data. Let's look at, for example, our trips data sets. So our trips data set at the source is stored within a bunch of like sharded databases. So when we ingest this data into Hadoop, we partition the data based on the notion of time, so on daily basis. Which means like a new trip happening today, it flows through this pipeline and comes to today's date and gets stored here. These are the boxes that were supposed to be green, by the way. The coloring is very messed up here. So the new trip from today happens here and gets stored here. So let's say you take a trip, it's $15, it gets ingested, it comes over here and gets stored. Now let's say you later look at the price and say, oh, $15 is too much, and you submit a support ticket that, oh, I'm charged more than I should have been, and like the driver sticker around or something. So they agree to change the fare back to $5. Now you have an update as a $5 on the same trips that needs to be ingested. But Hadoop file system doesn't let updates to happen. And at the same time, we were using those columnar file formats that also doesn't let you update. For columnar file formats, you need to have all your data, organize it per column, and flush it to disk. So you can do an update just one single day. So these are the yellow boxes I think that are here. So these are the updates that are coming. So if you look at these, the number of updates as we go back in time reduces, but you have a long tail of updates going back. In terms of fail, it usually happens within a few days because you submit a ticket within a few days, like let's say a week, it gets updated. But there are other types of updates that happens more than one like a week. For example, think about the way you rate your driver. So you rate your driver the next time that you take an Uber. So if you are a person who doesn't take Ubers on a daily basis, which I hope no one in this room is in that category, then you will gonna rate it, for example, maybe a week later, 2 weeks later, or even a month later. So we have updates coming all the time, and it goes back in time. And again, this can be because of like updates, like from the ratings, or it can be like, for example, they make tax adjustment at the end of the year, which affects all the taxes that Uber has like stored for the past 1 year. So backfilling, like these modification happens all the time. And this is why the update is a natural part of a data set that we have to deal with. Okay, so let's look at how we basically were able to absorb the updates at that time and why the data latency was 24 hours. Okay. So the way we were doing this at the time was we had all these data sources and we were streaming in all the changes, but we needed something here to absorb all these updates. And we used HBase at the time, which is a key value store that allows us to absorb updates. So we were getting all these changes, we put them in HBase, and every few hours we make a new snapshot, convert it into Parquet, put it into Hadoop, and swap the two tables. And this was working fine when we were having like a few petabytes of data, but then the data starts growing, and this becomes extremely time-consuming and very inefficient. I'll give you an example for our trips data sets. The job itself was taking 20 hours. So we could only update our trips once per day. And this is why the data latency was remaining at 24 hours. And again, this was it's not only the matter of time, it's also the inefficiency resulting of that, because let's think about you have a trips data table that is hundreds of terabytes. You have one record updated. Because of that one record, you have to recreate, really convert all those 100 terabytes into Parquet. But it was very inefficient and it was very time consuming. Okay, so let's look at how we solve these problems. So again, the main motivation for solving this problem was Hadoop becomes extremely popular, and it was basically it was serving a lot of services that relied on these data. At the same time, this was the first time that we were out of that firefighting mode, so we had time to go and study our data sets and our basically access patterns and see what exactly, what basic primitives we have to build, what services and libraries we have to build to solve the problem for long term. We didn't want to just stitch this up. Initially, we were hiding all these updates by having workarounds, but we wanted to build something that actually fundamentally solved the problems. So let's look at all these pain points and see how we solve each of them. The first one was scalability. So scalability, I mentioned there are two parts of that. It's HDFS scalability as well as ingestion scalability. So HDFS out of the box is working pretty fine for a few petabytes of data. When you get to 10 petabytes, 20 petabytes, name nodes start showing up all the pressure. And when you get to 100 petabytes, you definitely need to fix some of the problems, otherwise the whole thing would fall apart. So this is very complicated, but the good thing is there are a lot of other companies who did the similar stuff and they published the way they solve the problem. So the solution is time consuming, but it's pretty relative. It's pretty straightforward. And basically, you need to kind of find a way to federate your data. That can be done on the client side, on the node side. So it's some sort of federation, and making sure you monitor for small files will help you to scale HDFS at the core to 200 petabytes and beyond. And we have a very detailed blog post in terms of what exactly it is here. But I'll pass on the details here, and because refer to the blog post, and we can talk afterwards if you have any questions. But it's pretty straightforward how to do that. The other part is ingestion scalability. So this is the part I was saying, we had a bunch of Spark jobs that were bringing the data into Hadoop. It wasn't an actual platform. So when we scaled into several thousand tables, it was breaking every day. At the same time, okay, so let's do this. So let's look at how we solve the ingestion scalability issue. So the way we tackled the problem is we started building a real platform to solve that problem. That platform is called a project called Marmalade, that is open source if anyone wants to use it. And the idea was make it like a platform that is very pluggable and very modular and very generic, which means there is a platform that lets any source to any sync data transfer. And so you have a Marmalade, and you can have all these different sources. As long as you implement the source that connects to that data store, you can bring the data and you can have the sync at any other place. So we have sources from our Strata database, Cassandra, MySQL, Kafka, bringing all the data into Hadoop. At the same time, since it was very generic, we were able to provide it as a dispersal platform too, which means when the data comes into Hadoop, people process that data and creates new data sets, and Marmalade lets them get that data out of Hadoop too. Think about, for example, our Uber Eats. When people place orders for food, that data, the online services that serves Uber Eats, they store these data in Cassandra. The Uber Eats team bring the data into Hadoop every 30 minutes, every 1 hour. Then the data is in Hadoop. They run a bunch of machine learning models. So that basically they create a machine learning model that suggests new restaurants and new dishes based on your previous interaction. So they do that modeling, they update their model once per day. and then they use Marmalade to get that model out of Hadoop back into Cassandra so they can serve live traffic. And this is how when you log into Uber Eats the next day, you get recommendation based on what you did in the past. So this is how the whole Marmalade was basically organized. And again, it's an open source project. We have a detailed engineering blog post in terms of how it was internally implemented. So if you're interested, please have a look at that. At a very high level, we tried to keep it very modular. So we had a data source, a source connector, and a data stream connector. And everything in between was a bunch of converter that you can implement based on what you actually want to do. So this is like overall high level how the Marmalade was implemented. So that solved the first problem. Now let's get into the other problems. So the second problem was the data latency being too high. So our business is real time. We need the data in Hadoop as fast as possible. So, and I mentioned that we were doing a snapshot-based ingestion, which there's no way you can scale that to bring it down to like basically a few minutes. So we have to move that out of that snapshot-based ingestion into some sort of incremental ingestion. The other problem was the issue with updates and deletes on the previous data. So again, we couldn't get rid of Parquet because we needed some sort of columnar file formats to optimize the cost of the query as well as the cost of storage. And any columnar formats that we use, it's going to have the same issue. So we needed to provide support for updates and deletes somehow on top of the columnar file formats. And finally, the ETL and the modeling side. The ETL was also a snapshot. We needed to move that into incremental model. At the same time, think about the trips issue that I explained before. So we have trips coming in, and we have updates on the trips coming in from the past. So if you are a reader, a user of that tables, for you to see a trip from 6 months ago, which is stored in a partition from 6 months ago, is updated now, the only way you can do that is to do a full table scan, and then there is some notion of time to filter out the records that you need. And when you're dealing with huge amount of data, that's extremely expensive to do a full table scan. So many users were solving this problem by basically only focusing on past few days of data and ignoring any updates on the data before that. In other words, they were willing to sacrifice the correctness and completeness of their computation in order to avoid the extremely expensive table scans. So that's the fundamental problem here that we needed to solve. And now let's look at how we solve that problem. So the way we solved all these problems together was through a library that we built, and it's called Hudi. Hudi stands for Hadoop Asserts and Increment. It's a storage abstraction that provides you basically with two primitives. First, it lets you update and delete on top of the read-only, append-only columnar file format in HDFS. That's one primitive. The second primitive it provides is on the user side, that it lets the users to incrementally pull only the change data without worrying about when that happens in times. In other words, the reader of the trips table can get a stream of changed records, all the new and updated records, even if it's from 6 months ago, without doing a full expensive full table scan. In addition to that, Hudi also lays out the data on disk in an efficient way. It basically makes sure the files are large in size, they are well aligned with the HDFS block size, so it avoids all the waste because of that. And it also provides snapshot isolation, which means usually in the Hadoop world, you have a batch of data that you bring in, and you don't want to expose it partially to the users. Hudi gives you a notion of transaction, which means you bring all this data in, you write it to disk, and you can expose it to the readers all at once. So it provides all these functionalities to you, and it's a Spark-based library, so it's by nature horizontally scalable, and the good thing is it only relies on HDFS. You don't need any other technology to run with this. And again, for you guys, the good news is it's open source, and we have a detailed engineering blogs in terms of how it was implemented. So when we built Hudi in 2016, it was mostly based on our own data set, because we looked at our data, the way our data was like updated, as well as how people are accessing those data, and we come up with these primitives, and we build a library to solve those. So we open sourced the project in 2016. A few companies started using that, but later last year, in 2017, the GDPR requirements came out in Europe. So traditionally, a lot of companies that were relying on Hadoop, they were dumping data in Hadoop, and we said, okay, on the query side, we only access the data that we need. We let the other stuff to be there, and we just don't use it. But when GDPR came into play, they couldn't just leave the data behind. They have to actually go and clean and delete the data. which was extremely painful for a lot of companies because they didn't have this functionality built in. And so at that time, Hudi became a very popular project. And a lot of companies start using it and start basically contributing to the open source version of that because of the same issue. And this is exactly one of the main motivations that I mentioned. Look, you need to study your data sets and find the right primitives that solves the problem fundamentally. And then if you do that, later when something like GDPR comes out of nowhere, you have a solution that can support that. Okay, so let's look at what Hudi does at a very high level. So at a very high level, you have a batch of data, updates from your data store that needs to be brought into Hadoop. On the storage side, when Hudi brings this data into Hadoop, it basically obviously writes the data into some data files that can be accessed. In addition to that, it also indexes the data, so later you can pick up the data based on the specific row key. At the same time, when you later want to update that, it uses this index to find the data files that needs to be updated. Hudi also adds some metadata in terms of when the data was actually implemented, and this is how the readers can read the data based on the actual time that record was updated, regardless of when that data where and how that data is stored in the past. This is the chips from 6 months ago being updated today. On the reader side and the server side, Hudi provides different views for users to access this data. So one view is you can get the latest snapshot, what's the current latest values for that specific data sets. Also, you can also get a stream of change logs, which we call incremental pool, that we can pull out only the change records and updated records, regardless of what time that actual data is stored. So let's look at a little bit more in terms of how Hudi helps with us to improve our processing model. So if you look at the way the data is processed traditionally, there are two extreme cases. On one side, we have batch processing, and on the other side, we have stream processing. So batch processing is where you get a batch of records and you process them all at once. If you have your data stored in some sort of columnar file format, it's optimized for batch processing because you only need the data from this that you actually need, rather than reading everything. So it's great for large data sets because it's the only solution you can have on all your historical data and run it all together. It's also very well optimized for running extremely large joins. So if you want to, for example, join all our trips, historical trips, versus all our transactions, you can't do that in a streaming job. But batch job lets you do this stuff. It takes some time, but it's doable. But on the con side, it also, the data freshness and the data latency is pretty high. So I mentioned that it used to be 24 hours, so it's several hours at least that you have to wait for your data to arrive, as well as your query to complete. The other end, we have streaming processing. This is the processing when you process every row, one row at a time, so it's row by row. So obviously it's not as efficient as processing a batch of records all at once. At the same time, when you're processing one row at a time, you get the entire row, you have to decode the whole row, take a few columns or few fields that you need and throw away the rest. And in terms of, for example, large data sets, for example, our trips that I mentioned, it has hundreds of columns. This is very inefficient. You're decoding the whole 100 columns just to pick up one or two fields. So it's definitely less efficient compared to batch processing. It's usually optimized for a smaller data set in order of terabytes, and it provides very limited join support. You can do stream against stream joins, but what if one of the streams is not aligned in time? You want to go back in time. So the stream processing does not let you do a full support for joins across different tables. But on the pro side, it allows very low latency on the data, so you can have your data processed and available within a few seconds. And these are both basically captured within the traditional Lambda architecture that tries to manage both the streaming and batch jobs by having the streaming processing running for recent data and batch to backfill the state that you need from your previous data. So if you look into how I try to explain the streaming and batch, you can see that there are three main dimensions that you need to consider when evaluating these processing platforms. So the first one is data latency. This is how fresh your data is and as well as how fresh your computer result is. So that's one aspect that's very important for different applications. The other aspects that you have to look at is completeness, data completeness, which means how accurate is your data on this and how accurate is the result of your computation. And the third dimension that you need to consider is the cost of running that query, which means for a given latency and completeness, what is the actual cost of running a job, a query, in streaming mode versus batch mode. And most of the applications, they look at different parameters and they usually decide either on streaming or either on batch. And the threshold between deciding between batch and streaming is usually very, very high. Mostly it's like 24 hours. So if you have an application that needs the data to be processed within less than 24 hours, within an hour, in 5 minutes, the only way you can do that is using streaming. On the other hand, if you have an application that it's not time sensitive, you want it to be efficient both in terms of cost and in terms of like not worrying about running a streaming all the time, you can run it in batch mode. So you wait a day, the data lands, you run your job, and get the results back. So regardless of the approach you use, you are sacrificing something, which is you are either skipping updates or you are basically skipping the late arriving data in the processing side. So when we were building Hudi, we actually looked at different applications within Ubers and how they are using the data. And we tried to categorize them in different clusters. So this is so we skipped the cost at the time because it was our second priority. We focused on latency versus completeness. And if you look at this like 2D graphs, you can see that we have very separate clusters. So there are applications that are, by nature, they are well suitable to be running in streaming mode. Think about, for example, our search pricing. So search pricing is very real time. It has to look at what's happening right now, and it has to go and update the prices based on that. So definitely it's a perfect match for streaming use case. On the other hand, we have like some applications that are very good match for batch. Like think about, for example, backfilling the data from like 2 years ago. For some reason, they need to backfill something. Or there are data scientists running some query against like data from like 3 years ago. So these are not time-sensitive data, and they're optimized to run in batch modes. But if you look in the incremental side, there are a wide range of applications that are not streaming, not batch, and depending on how what persons like they decide at the time what technology was available, they either fall into either streaming or batch. A good example, for example, is fraud detection. So fraud detection uses historical data to find current frauds. So it's somewhere in between streaming and batch because it needs all the historical data to be accessible as well as the new data. So there are a lot of categories of application that falls into the incremental mode. And this was the motivation that we come up with like those primitives built into Hudi. So let's look into what actually incremental processing is. So incremental processing was our efforts to provide streaming style processing on batch data. For those of you who are familiar with Spark, Spark provides some notion of like called micro batches. So we call these mini batches. So these are mini batches that are running every few minutes. And the goal is to increase the efficiency and lower the cost, obviously, by reducing the threshold between streaming and batch processing. As I said, traditionally, 24 hours was the magic threshold to decide whether your application should be running in batch mode or streaming mode. With mini batching, we want to push that boundary and bring it down to 5 minutes, 10 minutes, something like that. So everything between 5 minutes and 24 hours, you can run it in mini batch modes. After 24 hours, you can run it in batch modes. Below 5 minutes, you can run it in streaming batch. And then the other goal was to increase the accuracy of the result by not dropping or skipping any data. Regardless of whether it's late arriving data or updates or deleting some previous data, you want to make sure that the result is as accurate as possible. For this to happen, we need two primitives to be implemented. One is the observed primitives, which means you need to be able to go and update and delete data from your data set in the past. If you guys are familiar with stream processing, this is very similar to the state store in stream processing. The problem with stream processing is that these state stores is limited in terms of, because of the space you have, in the memory that you have. So you can only store a few days of previous data in your state store. When you get into mini batch mode, you have the data written on this, so you can have an unlimited state store. You can have all the previous data on this and go and update those. The second primitive we did was the incremental proof. This is on the reader side. So if a reader is reading a table that has updates in the past, that reader, to be able to do this stuff efficiently, needs to get only the changed data and only access those and read those data and work on those, rather than doing a full table scan or accessing everything. And this is basically a log stream of the new or updated data, regardless of basically when that happens in time. So if you are familiar with when we do a stream processing, there's always a look-back window that people consider. This is the time frame that they consider updates. Any record that arrives after that, or is updated after that, you just basically say it's not active window, so we drop it. Okay. So yes, so in terms of the 3 dimensions that I mentioned, let's try to put streaming, batch, and incremental processing next to each other and compare them against these 3 dimensions. So first is data latency. So streaming, obviously, it's very fast. It provides second-level latency, so it has the best latency. And then we have incremental that we can run it every few minutes. And then we have the batch, which basically runs 24 hours on the clock. In terms of completeness, streaming obviously has much lower completeness, especially when in the case when you're having late arriving data or updates. Batch and incremental, you have all the data accessible, so they provide perfect completeness and accuracy on terms of principle. In terms of the cost, streaming, you're processing 1 row at a time, when in incremental, mini batch, and batch, you're running the stuff as batches, so it's obviously more efficient, so the cost is much better in terms of incremental and batch. If you want to compare them in a graphical way, the classical data processing solutions, the guideline was, if you need processing or access less than 1 second, use a traditional database, RDBMS, like MySQL, Postgres, something like that. If you need something between 1 second and 1 day, you rely on streaming processing, and anything above 1 day, you basically fall back into batch processing. The way we revise this guideline is by introducing the incremental mini batch processing, which means we have the same threshold between database and stream processing, but any application between 5 minutes and 1 day, we can efficiently be running an incremental mini batch processing. One other thing that we changed when we were redesigning our big data platform was we tried to standardize everything, which means like when you're building a super large scale data platform, you can't let exceptions happen in any part of the platforms. Let's take it 1 level higher and see what the goal is. You have different data stores, different tables at the source, and the goal is to provide an exact copy of all these tables in Hadoop all in one place. So if you think about these examples, we have these data stores. Again, let's keep it general. It can be a sharded one, non-sharded one, any sort of data store that you use. And the users put a bunch of basic updates in these tables. For example, row 1, column 1, value A, row 1, column 2, value B, row 1, column 2, value C, row 1, column 1, value D. So if you look at this data store, depending on when you look at it, there is 1 row key, there is column A, column B, and it has value A, B, C, D. So depending on when you look at it, you will see different values. When we bring this data into Hadoop, we get a stream of these change logs to bring into Hadoop. And for our users to be able to access these same data stores in Hadoop, we provide 2 views on the same data so that we can address different use cases on the user side. One view, we call it merge snapshot view, which basically shows the latest updates on each value. And this is where, because we have to absorb the updates, and this is where Hudi comes into play, because for the same row that we had previously value A, now we have to go and update the value D. On the other hand, we also provide a changelog history table, which shows you all the history of these changes over time. And the good thing for the users is that they can, the applications that rely to know all the changes in between, they can actually go and use this table. So when you look at these tables, you would only see the current latest value. By looking at this, you will see all the changes over time as well. So with that in mind, let's look at what incremental mode and latest mode in Hudi looks like. So think about like an upstream table that we're ingesting into Hadoop. So let's, again, we are ingesting this data in batch modes. So let's think like we go and ingest the first batch into Hadoop. So you have key 1, key 2, key 3, and they get ingested into Hadoop. So this is your table in Hadoop. And then let's say half an hour later, the batch runs again. It goes and gets second batch of data and brings it into Hadoop. And in this batch, we get an update on the first key 1, and we have a new value key 4 as well. So this is the table that is in Hadoop. Now, for the users to access these tables, they can pick on the same table. They can pick different nodes. The first node is called like latest node, which means they will get the latest value currently available for that tables. Which means if this was A and later changed to G, the users reading this table will want to see the latest value for this. At the same time, the incremental mode lets user to pass in a checkpoint timestamp and gets all the updated and added records after that. So for this specific table, assuming that the user has read already the tables at timestamp T0, if they pass in time T0, they would only get the records that are updated, like T1, or added after that time. And this is the difference, like how the Hudi provides incremental mode that makes users be more efficient by only accessing the data that has multiplied by the Cool. So let's look at our architecture after we built Hudi. So again, on the left, we have different sources of data. The changes on the upstream data stores were streaming to like the buffering space like Kafka, and there was ingestion jobs that running every 15 minutes to bring this data into Hadoop. The good thing is when we have Hudi here, we don't need to have something like HBase to absorb all the changes. We can directly go and update the data in Hadoop using Hudi. So this allowed the end-to-end data latency for our raw data brought down from 24 hours, brought down to less than 30 minutes. The data modeling, these are the readers of these source tables. So they were incrementally pulling only the changed data, and they were updating the same tables in Hadoop. So, and this was taking also 30 minutes. So by having Hudi added to the system, you were able to bring the end-to-end data latency to less than 30 minutes for raw data and less than 1 hour for the model tables. And this is like what we started, we released into production in the beginning of 2017. Our data size was over 100 petabytes, and our data latency came down from 24 hours to 30 minutes. And this was, by the way, big change for the business. A lot of applications that they didn't have access to data on time, now they could easily and efficiently access to fresh data in 30 minutes. And this is putting all these components together. So you have on the left, you have all different sorts of possible data stores. I explained the previous one, I summarized it, but here we have all Cassandra, Elasticsearch, Postgres, MySQL, sharded databases. So all these data sources, regardless of where it is, as long as the membrane has a connector to bring the data, they ingest the data, they use Hudi file formats to absorb all updates, release new data in one space, in one shot, and then the users can access this data in Hadoop directly through different core engines that we provide, or through other platforms that exist on top of this data. For example, we have machine learning platform, we have the visualization platform. These are the platforms running on top of this data. The idea is for the users to play around with this data and create new data sets in Hadoop, and then Membrane can let them take it out back into Cassandra or any other place that they want to take it out. And we have a centralized schema service that basically governs all this data across the company to make sure that the data across different services are always of highest quality and compatible. Okay, so this is what we currently are running in production. Are we done? Obviously not. So let's look at what are some of the projects that we're currently working on, what we're going to build next. So the main issue that we are currently having, we invested a lot in improving the data quality, but it's an ongoing battle. You have to keep pushing for that to be able to improve the quality for our users. So I'll give you an example. It's like I mentioned the centralized schema service, which was basically providing basic structural type checking on our data. But that's not what our users want. Think about, for example, a field is defined as age. And if it's defined as basically as integer, our schema service can make sure the value that gets into Hadoop in our data lake is of type integer. But it's an age. If we're having a negative value for that, doesn't make sense. Having a value of 1,000 doesn't make sense. So our users need beyond that basic type checking, structural checking. They need some sort of semantic checking. And this is what we're building next, to let users to define semantics on top of these data, to make sure the value, for example, for a field called age, is not only integer, but also within a reasonable range. So that's one effort that we're working on. The other effort that we are pushing for is, I mentioned that we have two different boards that we work, the online board and the analytical boards. And traditionally, there was some sort of disconnect between these two boards. So online board was primarily focused on making sure the trips can happen. And if someone opens the app, they can make the request and get the ride as soon as possible. And they were sacrificing from time to time in terms of the quality of the data or other stuff to make sure the users get the service they need. And then it was very problematic for us on the data side because we were having the data that was kind of incomplete or corrupted at the source. Then we had to bring it into Hadoop, and it was not doable because part of data was badly missing. And these were basically, the data was an afterthought at the time, and the focus was on serving the web traffic. As part of our ongoing efforts, we are trying to bridge the gap between the RPC world and the analytical worlds. In other words, if there is a schema defined for different services communicating to each other in the RPC world, we want to make sure the same schema is also enforced for the same data when it comes into data worlds. And anywhere in between that contract gets violated, we get notification as soon as possible rather than data. So that's one effort that we are pushing for. So I mentioned that with having Hudi, our first version of Hudi, we were able to bring down the data latency to 30 minutes. But that's, again, our business is very real time. So that's not where our data users want to be. So they want us to provide data latency even fresher than that in the batch world. So we are working on re-architecture in Hudi to provide data latency of 5 to 10 minutes. That's some ongoing works. And again, this is like, so our threshold right now for the user to decide whether they should use mini batches or streaming is like 30 minutes. We want to bring that further down to 5 minutes. Efficiency is the next big thing that we are working on. Again, I mentioned when I was talking about the dimensions that we had to give up on efficiency in order to be able to focus more on completeness and latency. But with the data growing, the cost of hardware for storage and compute is exponentially growing. Again, we are trying to go public, so there's every motivation to focus on efficiency. And this is the waste of resources in terms of storage or compute. So at some point, you have to focus on that and try to optimize those. So one thing that we are currently working on is to go beyond Hadoop. So traditionally, we were using Mesos for our online services and Yarn for managing our resources in Hadoop. So we introduced a project called Peloton, which is the unified resource scheduler for both online and offline services. And this is like making sure our services or boxes are utilized as best as possible over time, regardless of whether it's an online service or offline service. Hudi, again, is still a project that we're actively working on. So I'll give you a quick overview of like what we are changing within Hudi. So think about like Hudi, it's an abstraction library on top of the columnar file formats. So the way it works behind the scene is that you have a base like Parquet file with a bunch of records in it. Now you get an update on one of these records. So behind the scene, what Hudi does, it rewrites the files and applies the update as part of the rewriting and version these files. So behind the scene, you will have multiple versions of these files with updates being applied on top of those. And we have a cleaner that based on some notion of time, it goes and cleans up the old data. But as you can see here, it's not optimized in terms of the disk I/O, and because for one record, so we are trying. The goal is to make these files as large as possible in Hadoop. So we are aiming for 1 gigabyte files. So it's very inefficient to rewrite the 1 gigabyte files because of one single record being updated. So that's why we are building Hudi 2.0, which basically addresses this problem. Which means you have a base Parquet files. Any update that comes, you don't go and rewrite the base Parquet file. Instead, you write basically a raw file formats next to that base Parquet files, and you store these updates into that file. And we have an asynchronous compactor that goes and merges these two and generates a new Parquet file only when you have enough updates for new records to justify the cost of rewriting the files. And this would significantly reduce our write and read amplification in HDFS. It would also allow us to further increase the size of these files in Hadoop, as well as it lets us basically to provide fresher data with 5 to 10 minutes for our users. The good thing that when you have like the data written in both base Parquet files and in a delta file next to it within 5 minutes, the good thing out of that is that now you have options to expose the same data sets to different users with different with different trade-offs. So we talked about the users who are accessing this Parquet data. We call that read optimized, which means you have a columnar file format on this, and the users who are accessing this data only read the columns that they need. When we added delta files, the users have two options. If they are not sensitive to getting the recent data, they would wait for the compaction to happen, and they would read the new updated columnar file formats. Again, that's read optimized for that new tables. For the users who are very sensitive to the time and they want to see the updates, even if it's not written to the base Parquet files, they can do the merging of the delta files and the base bracket files on the query side. It's more expensive in terms of like processing, it's like a little bit more expensive, but it lets users access the data within 5 minutes latency. And the good thing is, the same data sets in Hadoop can be exposed to different users depending on the view that they need. So we call these read-optimized view as well as the real-time view. And we always have that incremental change log view that you can get the changes out. So that's in terms of what we do with Hudi. So let's try to wrap up this talk by talking about some of the lessons that we learned. So the first takeaway for you guys is that there's a lot of existing open source projects that like very nice products available open source if you want to build a big data platform. But the tricky part is you can't just take one architecture from Uber or any other big company and try to use it on your own place, because at some point you're going to see that it's not optimized for your own use case. So the main takeaway from this talk should be the fact that if you are thinking about building a big data platform, spend some time, understand your data sets, what does it look like and how users are accessing those, and pick a solution and architecture based on what you actually need, rather than copying what I explained or copying what other companies have explained previously. So that's one takeaway. And the good thing with that is, again, I mentioned that GDPR requirements, it was a really, really big thing for many companies in the Bay Area, because the data was by nature were not supposed to be updated, but the regulation actually asked them to go and update the data. For us, it was very straightforward because we had the right primitives at the time to go and let the teams to go and update the data. So if you build the right primitives, it pays back and it solves the problems because you're building something based on the nature of your data sets. The second thing that is that data quality is going to be an ongoing effort. So there's a very tiny blurry line between having a data swamp and an effective data lakes. So the idea that 5 years ago, the idea was put everything like Hadoop, it's scalable, and you later figure out a way to basically use the data. If you don't invest into data quality from day one, you will end up with a data swamp that you have all the data, but it's not usable. No one can actually find what they want. Or they can find it extremely hard way, and a lot of man-hours spent to find the data or actually process data. So definitely stay in terms of like data quality by enforcing the schema from day one, by enforcing semantic checks as well as basic type checks, by trying to make sure the schema has basically defined in the best possible way. Which means try to avoid like generic types. Like for example, don't give that user to define strings. People can have typos. It's the nightmare afterwards to fix that issue or figure it out. Try to use like predefined enumerated values as much as possible. Try to enforce the documentation. At some point we had several hundreds of pairs defined in our schemas, and they were very incompatible. So the users who were trying to find a pair for a tree, they didn't know what tree to use or what currency the pair is at because it was not documented well. So make sure the documentation is mandatory. Standardize the schema names. Standardize the way fields are defined. Standardize your core entities and force users to use those core entities in their schemas. And in other words, like standardize everything. If you're building a big data platform, don't let exceptions happen. The moment you let one exception happen, that's opening doors to tons of issues coming out of that. And that would result in tons of unhappy customers within the company. The other takeaway is ensure that you have basically some retention policy from the beginning. It's really, really hard to change the mindset of your data users by saying, oh, the data beyond a certain days is going to be deleted afterwards. Even if you want to have a retention of unlimited, make sure that users are aware of there is a retention which is currently set to unlimited. It is a big mindset change within the company, but try to make sure it happens as soon as possible. The other thing is store the metadata about your data. This is data about your data. For example, who brought in what type of data? What's the relationship and lineage between different data sets? What's the content of these data? What's the data access patterns? These data, when you scale, it becomes a very tricky thing to later figure out. If you want to make any change, and you don't know who brought in the data or who is using it, it's really hard to make any changes. Invest in a good data pipeline monitoring. So I mentioned freshness, latency, completeness like through this talk, but these are actually, they look very similar, but they're very different terminology. So define your terminology and build a really good data pipeline monitoring around those metrics. And this would help you detect data issues before users start complaining about this, which is going to save you a lot of times and angry users. Stay away from user-defined values. it's almost guaranteed to break at some point. So move away from user-defined fields and try to rely on system-defined values. I'll give you an example. When we were bringing tricks data in, we were relying on the actual field that the services upstream put in for the time of the trick happening. And there, when we start running that in production, we saw multiple cases that value didn't make sense. It was null or it was set to the wrong timestamp. So we moved away from that by relying on the timestamp on the data store that actually stores that transactions. And that becomes, again, there's a few seconds or even a few minutes in corner cases difference between these two, but it guarantees to not be violated because of the system level fields. And finally, pay attention to the notion of time in terms of your data. I mean, when we are talking about like data pipelines, there are very, very different timestamps involved. For example, when the actual trip happens, when the actual trips was stored in the upstream data store, when that upstream change was ingested into the pipeline, when that was stored in actually Hadoop, when the users run the query to access that. These are very different notion of times, and a lot of times users are confused by these. So try to make sure that it's as clear as possible to the users so they don't make mistakes. So finally, if you are interested in any of these projects or efforts that I talked to, definitely come and talk to me. We're hiring for all our offices across the board. I'll be happy after this talk outside if you want to come and talk to me. If you want to learn more about the details, we published a blog post like a month ago in terms of our big data platform journeys. It's an extended version of this stuff, so, and it has more examples. It's a very nice split. If you want to read more about the details, definitely check this out. We also have more technical blog posts in terms of how memory was implemented or how Hudi internally works. These are all available on our engineering blog posts, so definitely go and check them out if you want to know exactly how stuff works behind the scene. And with that said, I think I'll wrap it up here. Let's take a few questions and then I'll stay up afterwards. If you guys need to leave, please feel free to go. I'll stay here if you want to talk to me afterwards. I'll repeat the question.
Okay. Can you show please this slide with your final architecture?
Oh, fine. Oh, sure.
And the question is, have you considered using Kafka Connect instead of inventing this Marmarai framework?
Correct. So there are two things for that. Correct. Kafka Connect is a very actually, yes, we did consider that. The problem is when we built Marmarai, Kafka Connect was not mature enough. That's number one thing. And the second thing that we are using Marmarai is because of the way we integrate. So this is the one that you wanted?
Yes.
So the reason that we are using Marmarai is because it's pretty well integrated with Hudi file storage format that we use. So the combination of two makes it much, much easier for us to use. But nothing prevents it. Kafka Connect is actually pretty good state right now. I know other companies using that. So you can definitely look into that. And I'm not setting Marmarai as the only options to use that stuff. I'm just, this is what I was saying, like there's no single solution for your company. You need to compare them side by side and pick the one that's right for your use case. We can talk about the details afterwards.
It's just natural with this flow, and it will bring you even better real-time characteristics as opposed to current mini batches.
So the what?
I said that it naturally fits this architecture, and it will bring you even much better real-time characteristics as opposed to current mini batches in Spark.
Correct, fair enough on that side. But if you look at so the tricky part is if you look at the way it does have a Parquet writer too, but the way the Parquet writer works for that, it recreates the whole data sets for you, right? So if you want to use it with something like this, you need to replace that Parquet writer with the Hudi writer, or you have to use something like this. It does, behind the scene, it actually rewrites all the Parquet data. It doesn't absorb the updates basically. It doesn't have support for updates and things. Yeah.
Can you elaborate on what Hadoop distribution you use, whether you have something custom or you use something that's more...
So we started by using like the packaged products from different companies provide, the one in the but we found that they're focused mostly on stability and making sure all the components they provide are well meshed together. So we are running the stuff at the very high end, at large scale. So we need to basically get the new patches from open source to actually be able to patch this stuff. So we moved out of using any company certified version of these softwares, and we are using vanilla Apache versions.
And one more question, can you elaborate on whether or not you use data locality for Spark jobs, or?
We do actually. So we separated our compute layers from our storage layer, but we rely on Yarn to provide us data locality. Data locality is actually a big part of Spark and Hadoop ecosystem. Correct.
Thank you.
Is it an architecture or is it data center?
Correct.
So how do you synchronize data between data centers? Because in case of failure, the tree might be started at one data center and then
So the way we address the data consistency across data centers, so our analytical data boards, it runs in active modes, which means all these pipelines run totally independent in different data stores, in different data centers, but we rely on our upstream data source to be synced across data centers. So we build services that, for example, I mentioned the sharded database we have here to store the tubes data. We have some part of that sharded database, for example, in data center 1, some part of data center 2. We build services that synchronize these two data. So the source data is synchronized, and then when you ingest them independently in different Hadoop boards, the output data will also be automatically synchronized.
A short question about what kind of recommendation regarding supporting platform HTTP or Caldera, what's better to supporting infrastructure side, monitoring for Hudi?
So Hudi is an abstraction library. As long as you have Spark running, you can use Hudi. So both HTTP and Cloudera works perfect. By the way, they joined, so it's like a problem solved. So it works perfectly well. We were using like both of those. It was working very fine. So as long as you can have a Spark platform running, you can use Hudi. Hudi is a Spark library. You can use it within Spark.
Anyway. And second question, to change log you are using format Avro.
Okay.
Is it some problem with Parquet?
No. So the project, so we definitely have Parquet at the core. So we have Parquet files of 1 GB files, right? We have those Avro files for records that are updated. One record gets updated, we don't go and update that Parquet files. We write that one single record in an Avro files next to that base Parquet files, and when we have enough of those records that justifies updating the Parquet, we go to and compact those. So they are sitting both together. We did not replace the Parquet with Avro. They are both sitting there for different reasons.
Thanks.
Currently running Devoxx every 24 hours. What are you doing next?
No, we're running it right now once every 15 minutes.
Oh, you're actually...
So our batch of our ingestion platform runs every 15 minutes, but that's why we mentioned that latency is like 30 minutes, because we want to have headrooms with one failure. So our average latency is actually around 15 minutes. In our next version, we are moving to the mode that we are running it every 5 minutes.
True, that's orientation, but you set up like whole batch job, which actually does the snapshot presentation.
You're talking about the ingestion part or the user part?
The actual, the 24-hour batch job. Do you still have that?
No, we do not. We replaced it, but exactly. We moved out of that one big job that was running it once every 24 hours to a bunch of small ones that are currently running every 15 minutes, and we are moving to a bunch of smaller ones that runs every 5 minutes.
Oh, okay, so you actually get rid of
Oh yeah, that was the whole goal with this project. So we totally got, so that job, to give you an idea, when we started, we were having around